Hello everyone, welcome to the week 9 problem solving session for the pattern recognition and application course. I am Tonuka from ISC Bangalore and I am a PhD student over there in the electrical engineering department. So in today's session we will solve some problems about designing the discriminant functions for classifier design, and we will also solve some problems on neural network. So let us start with the first problem. As the problem reads, for a 3-class problem following are the decision boundaries. So for a 3-class problem, let's say omega 1, omega 2 and omega 3 are the 3 classes, and the decision boundaries between the 3 classes, between class 1 and class 2 and class 3 and class 1 and class 3 are given. So the 3 equations are given. So G12 is basically the decision boundary between the classes 1 and 2, or omega 1 and omega 2, and that decision boundary is given by x1 equal to 0. So as you can see from the different functions of the decision boundaries or equations of the decision boundaries, there are 2 variables involved, x1 and x2. So we can see that the feature space on which we are drawing these decision boundaries, that is a 2D feature space, and on that we have 3-class problem. So we have 3 class boundaries. So first one, as I said, the boundary between class 1 and class 2, which is G12, that is given by x1 equal to 0. The other one, the next one, G13, which is the boundary between class 1 and class 3, that is given by x1 minus x2 equal to 0. And the last one, G32, is given by x1 plus x2 equal to 0. So this is the boundary between class 2 and class 3. So these are the 3 decision boundaries. Now since it is given as the decision boundary, so if you just take the value of, let's say, G12, which is x1. Now the decision boundary is x1 equal to 0. So if a point satisfies the equation x1 equal to 0, then that is lying on the decision boundary. But if the point is such that the value of G12, that is the value of x1, is positive, then it is on the positive side of the decision boundary, and otherwise it is on the negative side of the decision boundary. Now for each of these equations, so positive side is for one class and negative side is for the other class. For example, with G12, the positive side is the class 1 and negative side is the class 2. Like that, G13, the positive side, when you compute x1 minus x2, if you get a positive value, that side is belonging to class 1 and the negative side is belonging to class 3. Like that you have, and the final decision regions are selected such that the intersection of these regions of which correspond to a particular class, the intersection of these regions gives the final region of that particular class. So let us so the question here is, using these functions you need to classify the following unknown feature vectors. So before going into the classification, first let us draw the decision boundaries and see which region of the feature space belongs to which class. So as I said, this is a 2D feature space. So we will have, let's say, x1 along the horizontal axis and x2 along the vertical axis. Now the first equation, G12, the decision boundary between class 1 and 2, is given by x1 equal to 0. So x1 equal to 0, that line, that straight line is basically this one along the vertical axis. This is basically G12. Okay. Now The next one is G13, which is x1 minus x2 equal to 0. So, that line will be so this is x1 minus x2 equal to 0. So, this will be this straight line passing through the origin with a slope of 1. This is G13. And the last one is G32 is x1 plus x2 equal to 0. So, let me take this color. So, that one will be this line. This is G32. Now, for let us consider the first decision boundary G12, that is x1 equal to 0. Now, if you need to decide which side of this decision boundary belongs to which particular class, right? So the right side of the decision boundary, if you take a point from, let's say, here, and then x1 is some positive value and x2 equal to 0 at that point. If you put this value in the equation of G12, which is x1, so they get the positive value. So that means this side, the right side of G12 is the positive side and left side is the negative side. So if the value of this function G12 evaluated at a point belonging to the right side of G12 is computed, then that will give you positive value. So positive value means that part is class 1, or let us say omega 1. So this side is your omega 1 and this side is your omega 2. Okay. Similarly, we will have to see for each of the decision boundaries. So each decision boundary is basically dividing the entire feature space into two half spaces. Each of the half space is belonging to one class. So now if you see for G13, the equation is x1 minus x2. If you see G13, let us say we take the same point here, the same point, let us say this one. So x1 is some positive value, x2 is 0. If you put that value, since this is x1 minus x2, so it will give you some positive value. So G13 will be positive on this side. Okay. So the positive side is for class 1. So since this is G13, so positive will be the class 1 and negative side will be the class 3. So this side is class omega 1, this side is class omega 3. Similarly, we will have to do for G32. G32 equation is x1 plus x2. So if you take the same point, then x1 is positive, x2 is 0. So overall it is a positive quantity. So this side, the right side of this line, that belongs to the positive side. So that is the omega 3 side and the left side is omega 2. So these are the divisions based on each of the decision boundaries. Now to finally decide which region belongs to which class, we will have to take the intersection of the regions. So according to G12 boundary, the right side is for class omega 1, and according to G13, that right side is class omega 1. So if we take the intersection of these two regions, what we will get is this part. This part, right? Will get this part. So this is basically our omega 1, this region. Now if you see for omega 2, that is the left side of the G12 line and also left side of the G32 line. So, we will have to take the intersection of these two regions. So, again what we will get is this. So, this is class omega 2, right. And lastly, for omega 3, so that is the left side of G13 and the right side of G32. So, you will have to take that intersection, right. So, it will be this part. This will be your omega 3. Okay. So, this is how the entire feature space is distributed among the different classes. Now, if you are given an unknown feature vector, you can just see at which part of the feature space that point is belonging, and you can simply classify the feature vector into the class to which the particular region belongs. For example, the first feature vector that is given is 5 minus 1. So, 5 minus 1 will be somewhere here, let us say it will be somewhere here, 5 minus 1. So, as you can see, as we already have obtained that this region belongs to class omega 1. So, we can say that this unknown feature point belongs to class omega 1. Okay. Similarly, if you take the next one, the point is minus 1 minus 1. So, where will it belong? It will belong somewhere here. So, this region belongs to class omega 2. So, this point will belong to class omega 2. This is minus 1 minus 1. This will belong to class omega 2. Similarly, if you take the next one, 2, 3. 2, 3 will be somewhere here. This is 2, 3. So, this region is for class omega 3. So, 2, 3 will belong to class omega 3. And the last point that we have is minus 1, 5. So, minus 1, 5. This will also be somewhere here, minus 1, 5. So, this will also belong to class omega 3, element of class omega 3. So, as you can see, the first one belongs to class omega 1, then minus 1 belongs to class omega 2, and the remaining 2 points 2, 3 and minus 1, 5 belongs to class omega 3. Both of these belongs to class omega 3. Okay. So, here as you saw, the entire feature space is distributed between these 3 classes. So, any portion you take from the feature space, that will belong to one of the classes, but that may not always be the case. It may be the case that some regions do not belong to any of these classes once you take the intersections. Okay. Let us see one such example. So, here the decision boundaries I have changed. So, the first one and last one are the same. So, x1 equal to 0 and x1 plus x2 equal to 0 are the same, but G13 has been changed to x2 equal to 0. That is the new decision boundary for this class. This is the changed one. So, if we change this, and then again we are asked to classify the same 4 points into the 3 classes. So, now if we plot these boundaries again, we can see how the region looks like in this case. So, this is again the entire feature space. this is x1, this is x2, and your G12 is again the same. This is your G12. Your G13 is x2 equal to 0 in this case. So, this is along the horizontal axis. This is the axis. This is the boundary G13, and the last one G32 is again the same, x1 plus x2 equal to 0. So, that one will be again this one. So, this is actually passing through the origin. It shifted a bit in my drawing, however, it is actually passing through the origin. So, this is your G32. So, as we have already seen in this previous example, that for G12 the right side belongs to class omega 1 and left side is class omega 2. So, this side is class omega 1, this side is class omega 2, because on the right side x1 value is positive. So, G12 value will be positive on the right side. So, positive side is G1, I mean the class 1. Now, let us see G13. G13 is x2 equal to 0. Okay. So, if you take this horizontal boundary G13, so on the above this line x2 is positive. So, that is the positive side. So, the positive side will belong to class 1. So, omega 1, this side is class omega 1 and this side is class omega 3. And for G32, as we have already seen, this side is omega 3, this side is omega 2. We have already seen that in the previous example. So, now here if we take the intersections. So, omega 1 is the right side of the boundary G12 and above the boundary G13. So, if you take the intersection, this is just the first quadrant. So, basically this first quadrant will belong to class omega 1. Now, for class omega 2, you see it is the left side of the G12 boundary and the left side of the G32 boundary. So, if you take that, the intersection for these two regions, then you get this. So, this is the omega 2, and if you go for the omega 3 class, so it is the downside of G13 and the right side of G32. So, downside of G13 and right side of G32. So, the final region will be this one. This is omega 3. This region belongs to class omega 3. So, you see there are two regions which are still white. This is one region and this is another region. So, these two regions do not belong to any of the classes. Okay. So, these are basically the ambiguous regions. If the point belongs to this region, then you cannot tell which class it belongs to. Now, if you try to classify the same points, let us say 5 minus 1. So, the 0.5 minus 1 will be somewhere here. So, as you can see, this point will belong to class omega 3. This is 5 minus 1. So, this will belong to class omega 3. Next is minus 1 minus 1. That will be somewhere here, minus 1 minus 1, and as you see, this region belongs to class omega 2. So, this will be element of class omega 2. The third point is 2 3. 2 3 is in the first quadrant, somewhere let us say here. The first quadrant belongs to class omega 1. So, 2 3 is also belonging to class omega 1. And the last point is minus 1 5. So, that will be somewhere in this region, minus 1 5. So, this is a ambiguous point for this particular set of decision boundaries. Minus 1 5 is an ambiguous point. So, you see in the previous example, with the previous set of decision boundaries, all the points were belonging to one of the 3 classes. You could classify all the points in the feature space to one of the 3 classes, but with this set of boundaries, there are some ambiguous regions, and the points belonging to those regions cannot be classified in any particular class. Okay. So, this is an example of multi-class classification using discriminant functions. Now, let us move on to the next concept. So, the next question that we have is, which of the following statements is true for KNN classifier or K nearest neighbor classifier? The first statement is the classification accuracy is better with larger values of K. And the second statement is KNN does not require an explicit training step. And the last two are both A and B are true and none of the above is true. So, before I explain the answer, will any of you like to volunteer and say what the answer will be? So, will it be option A, B or both A, B or none of the above? Anyone if you want to try. Okay, so the first statement that we see here is the classification accuracy is better with larger values of K. This is indeed true. So, what you do in KNN classifier is when you have a point that you need to classify, you take the distance of that point with all the training samples and you select the lowest K number of distances, and among these so you have selected K training samples which are nearest to your unknown sample. Now, you see which classes these K samples belong. So, the class to which majority of these samples belong, you classify your unknown feature vector to that particular class. So, let us say if you have one NN which is K equal to 1, you are just taking the closest neighbor from the training set and classifying your unknown feature vector to the class to which that closest neighbor belongs. In that case, that closest neighbor might be an outlier, and it might be the case that though your unknown feature vector is closest to that particular training sample, but it is actually far from other samples of that particular class, and it is actually closer to more number of samples in the other class. But since you have one outlier in the training samples and it turns out to be that your unknown sample is closest to that particular outlier, so you can classify it in a wrong class. Okay. So, once you have more samples, you are considering more training samples which are your nearest neighbors for the unknown feature vector, then there is the chance of this thing happening is less. You are considering the contribution or considering the opinion from more number of training samples that what this region should belong to. So, as you increase, as you take more opinions, as you take the contribution from more training samples, it is less likely that you will be classifying the data in based on some outliers. So, it is the accuracy will be better when you have larger values of k. So, the first option is indeed true. The second option says KNN does not require an explicit training state. This is of course true, because in KNN you just determine the distance of your unknown feature vector with all the training samples, and you take the lowest k number of distances, and you the class to which majority of these k samples belong, you classify your unknown feature vector to that particular class. So, there is no training involved in this, you just need to compute the distance and classify based on that. So, both option A and option B are true for this particular question. So, both A and B are true in case of KNN classifiers. Okay. Now, let us move on to the next problem or the next MCQ, which says a multi-layer perceptron network is an example of supervised learning, unsupervised learning, semi-supervised learning, or none of the above. Please, any of you want to answer? This is a very simple question, so I guess both of you can or all of you can answer this. Anyone who would like to volunteer? Okay, since I do not get any answer, so I'll explain. So, this is basically a supervised learning, because in multi-layer perceptron network what we do is we have some training samples, and when we are going to train the network, so we use the training samples to train the network, and for these training samples we know what would be the desired output of this particular network. So, we know the output, the target output which is called, and based on that output we try to compute some error and try to adjust the weights of the perceptron network. So, this is called supervised learning, because we have that supervision that what should be the desired output. Once you have that supervision, based on that you are trying to learn your network. That is, you are given that this should be your output, and you are getting this output. So, this much is the error. So, you should adjust according to that. So, that supervision you have the labeled training samples. That is why it is a supervised learning. In case of unsupervised learning, you do not know the target output, or in case of, let us say like classification, you know the classes, but in case of unsupervised learning you do not know the classes, you just know the feature vectors, and you need to, let us say, segregate them into different classes, which gives rise to the clustering problem. Or you can also have semi supervised learning approaches, but this multi-layer perceptron network is definitely a supervised learning approach, because you know for each of your training samples what should be the output, or you have labeled training samples. I hope the idea is clear now. So, I will move on to some problems on neural networks. The first problem that we have is, consider the unit shown on figure 1. So, as you can see in figure 1, we have a neuron. The inputs to the neuron are x1, x2 and x3. So, it is taking a 3D feature vector as input, and the weights corresponding to each dimension of the input feature are omega w1, w2 and w3. And the cell body is denoted by denoted by V here. So, V is basically the weighted sum of these input features. So, basically here V is your summation Wixi I equals to 1 to 3. That weighted sum is here denoted by V. And finally, you have the output y, which is applying some nonlinearity or some activation function phi on the value v. That is your final output. So, this is one unit or one neuron that you have. Now, it is said that suppose that the weights corresponding to the 3 inputs have these values. These are the 3 weight values. W1 is 2, W2 is -4 and W3 is 1. So, the 3 weights. So, this is basically you have already learned the weights of this particular neuron, and this is the weights that you arrived at. And the activation of the unit is given by the step function. So, if your V value is greater than equal to 0, your output will be 1, otherwise it will be 0. Now, it is asked that calculate what will be the output value y of the unit for each of the following input patterns. So, in the patterns you have 1 0 0, 0 1 1, 1 0 1 and 1 1 1. So, P1, P2, P3, P4 are the 4 patterns that you have, and you have to compute what will be the output when you give any of these pattern as the input to this particular unit. So, let us try to see this. So, as we have already written, the equation of V is summation I1 to I equal to 1 to 3 Wi xi, and your final y value is phi of V. Okay. We are applying the step function on V. So, if we simplify and write this, so y is phi of V, that is equal to phi of W1 x1 plus W2 x2 plus W3 x3, right. Now, you have W1 is 2, W2 is -4, W3 is 1. You can simply put these values in the equation. So, I put W1 equal to 2, W2 equals to -4 and W3 equals to 1. So, this is my input output relation for this particular unit. Okay. This is the input output relation. Now, so to compute what will be the output for any particular pattern, you can simply put that pattern feature values in this, or x1, x2, x3 values for one particular pattern in this equation, and you will get the corresponding output. So, the first pattern P1 that we have is 1 0 0. So, P1 is 1 0 0, that is x1 is 1, x2 is 0 and x3 is 0. So, for this if you compute y, that will be equal to phi of, here we are putting x2 equal to 0, x3 equal to 0 and only x1 is equal to 1. So, this will be phi of 2, and phi is your unit step function. So, if the value, the input to the phi function is greater than or equal to 0, the output will be 1, otherwise it will be 0. So, here you have the phi of 2, so the value will be 1. So, for the pattern 1 0 0, the output of your neuron will be 1. Okay. Now let us see the next pattern. This is 0 1 1. P2 is 0 1 1. So here you will have again y equals to phi of x1 is 0, x2 is 1 and x3 is 1. So you have minus 4 plus 1, that is equal to phi of minus 3. Now you have negative value in the function, within the function. So phi value for negative, it will be 0. Okay. So for the second pattern 0 1 1, the output of your neuron will be 0. Now let us move on to the third pattern, which is 1 0 1. Again your y, if you put the values, this will be phi of x1 is 1, then x2 is 0, x3 is 1. So phi of 2 plus 1, that is phi of 3. Since 3 is a positive quantity, so this value of phi will be equals to 1. And the last pattern we have is all ones. So P4 is 1 1 1. For this, if you compute y, that will be equals to phi of x1 is 1, x2 is 1, x3 is 1. So you have phi of minus 1, right? For if since minus 1 is a negative value, so the output will be 0. So for the pattern P4, which is 1 1 1, you have the output of your neuron as 0. So for the 4 patterns P1, P2, P3, P4, the outputs are 1 0 and 1 and 0. Okay. So this is how you compute the output of a single neuron, when you know the weights as well as the activation function. This activation function, here we take the step function, it can be any other function which is differentiable. So let us see one more example. So here it is said that assume a single neuron with 3 inputs and single output. So it is a same neuron as before. So you have a neuron with 3 inputs and 1 output. 3 inputs, let us say x1, x2 and x3. The corresponding weights, let us say w1, w2 and w3. You get the sum here and output here. Okay. So what will be the equation of your V? V will be equal to w1 x1 plus w2 x2 plus w3 x3, and the final output you get is y is phi of V, where phi is the activation function. Now in the question, let us see the question again. So you have a single neuron with 3 inputs and single output as we have drawn. Now the weights of the neuron are also given. So the weights to the neuron are 4, 5 and 6. So W1 is 4, W2 is 5 and W3 is 6. So you can simply put these values in the equation of V and simplify it. So your equation of V will become 4x1 plus 5x2 plus 6x3. Then the question says assume the activation function is linear with a slope of 4. So it's basically y equals to 4x, okay, or here your input is V. So your y is basically 4V, right, because this is a linear equation with slope 4. So your final output y will be equal to 4 times V, that is equals to 4 times 4x1 plus 5x2 plus 6x3. Okay. This will be your input output relation. Okay. Now the question asks what will be the output for the input pattern 4, 2, 3. So, your x1, x2, x3 values are 4, 2 and 3, and you will have to compute the output y for this particular input pattern. So, if you put those values in this equation x1, x2 and x3, what you will get is, so your x1 is 4, so 4 into 4 plus your x2 is 2, so 5 into 2 plus x3 is 3, so 6 into 3. Okay. You can simply compute this to get the final answer. So, let us see this. This will be 4 into 16 plus 10 plus 18. So, that is equals to 4 into 44, and that will be equal to 176. So, if you have this particular neuron with this particular weight values and this activation function which is linear with slope 4, then if you give 4, 2, 3 as your input pattern, at the output you will get 176. Okay. I hope this is clear to everyone. So, if you have any questions at any point, you can write it in the chat or unmute yourself and ask. Now, let us move on to the next question. So far we were seeing only a single neuron. If the weights are given, activation function is given, then given an input pattern, how to compute the output. Now, let us say the network has multiple neurons or multiple layers also. So, this figure here, this is basically a MLP, you can say this is an MLP, or it is also called feed forward neural network, with the first square layer, square neurons. This is for the input layer, this is the input layer, and this final neurons, these form the output layer, and in between you have one layer of neurons. This is basically your hidden layer. So, this you have a feed forward neural network like this. Now, let us see. The question is, a weight on connection between nodes I and j is denoted by wij. So, that is W13 is the weight on the connection between nodes 1 and 3. Okay. So, if that is the case, then the following table lists all the weights in the network. So, in that network all the weights are given, and it is said that each of the nodes 3, 4, 5 and 6 uses the following activation function. Again, the unit step function is used as activation function by all the neurons in the hidden layer as well as the output layer. The input layer ones do not have any activation function, because the input layer neurons just take the input and feed it to the next layer. So, here V is the weighted sum of a node, as we also saw in the previous examples. Now, each of the input nodes 1 and 2 can only receive binary values, either 0 or 1. In that case, calculate the output of the network, that is y5 and y6 for each of these input patterns. So, let us first draw the network ourselves and simplify the thing. So, this is the network that you have. So, you have two inputs, let us say x1 and x2. This is coming to the input layers, node 1 and node 2, these are node 1 and node 2. Then in the hidden layer you have node 3 and 4, this is connected, this is connected, 2 is again connected to both 3 and 4. And in the output layer you have again two neurons, 5 and 6, again it is 3 is connected to both 5 and 6, 4 is also connected to both 5 and 6. From 5 and 6 we have got the outputs. So, let us denote the output of each node by y. with the suffix as the number of that particular neuron. So these are the outputs for the 4 nodes y3, y4, y5, y6 for nodes 3, 4, 5 and 6. Okay. Now the weights are also mentioned in your question. So this particular connection, this is the connection joining node 1 to node 3. So here it is said that node W13 is the weight on the connection between node 1-3. So W13 is basically the connection, the weight on this particular connection, right? This particular connection. So as you see, W13 value is -2. So this weight is -2. Let us write down all the weights on the network itself. That will be easier for further computation. So then we have W23 is 3. So that will be the weight on the connection from node 2 to node 3. So this connection has weight 3. Okay. Similarly, W14 has the value 4. So that is the connection between the nodes 1 and 4. So this particular connection, this one is between 1 and 4, and the weight for this is W14, which is 4. And the last connection in this layer, which is this one between the nodes 2 and 4, so that will be W24, which is -1. So this is -1. Okay. So you have got all the weights connecting the input layer to the hidden layer. Now let us see the weights between the hidden layer and the output layer. So the weights between the nodes 3, 4 and 5, 6. So let's take the first connection. This is the connection between node 3 and node 5. So the weight will be W35, that is given as 1. So this is 1. Then the connection between node 3 and 6 will be W36, that is -1. So this is -1. This is -1. Then the weight between the nodes 4 and 5, that will be W45. W45 is again -1. So this is also -1. And the last connection, this one is between 4 and 6. So it will have the weight W46, which is 1. This is 1. So you see, you have got the weights for all the connections. Now let us try to write down the equations of the outputs of each of these neurons. Y3, that is the equations of Y3, Y4, Y5 and Y6. Okay. So you can see in the input layer, so the neurons in the input layer do not do any operation, it just takes the input and passes it on to the next layer. So the output of node 1 is also x1 and the output of node 2 is also x2. The input and output are the same for these two particular nodes. So now if you want to write y3, so y3 is for the third node. So the third node is connected to the first input node, that is the node 1 with the weight -2, and to the node 2 with the weight 3. So the weighted combination that it will perform, which we denoted by V in the previous example, that will be -2x1 plus 3x2. So this weight into this particular input plus this weight into this particular input. So the weighted combination will be -2x1 plus 3x2. That will be the weighted sum that will be computed within node 3. Now after computing this weighted sum, it will also take the it will also apply the activation function on top of it. So it will apply the function phi on top of it. So here also phi is the step function. Okay, so it's already 5, but since I started late, 10 minutes late today, so I'll continue and complete this problem. So like that, you see, this is the equation for y3. So it is the weighted combination of x1, x2, then application of the activation function, as you saw for a single neuron. Okay. Similarly, you can write y4. So for y4, this is also will be phi of some weighted sum, and that weights the two inputs that are going to node 4, they have the weights 4 and minus 1. So here the weighted sum is 4x1 minus x2. Okay. Now let us see node 5, the output of node 5, that is y5. Here the inputs are y3 and y4 is going as input to the node y5, and the corresponding weights of the connections are 1 and minus 1. So the weighted sum that will be computed at y5 are, the y5 is y3 minus y4, because y3 multiplied by this weight, which is 1, and y4 multiplied by this weight, which is minus 1. So y3 minus y4, and it will apply the activation function. Similarly, you can compute y6. So y6 is also getting the inputs y3 and y4. y3 is connected to to the 6th node by the weight minus 1, and y4 is connected by the weight 1. So the combination that will be computed here is minus y3 plus y4, and you will apply the activation function on top of it. So these are the equations for the outputs of each of the neurons. Now you have given some patterns, so some values of x1, x2, and you will have to compute what will be the output, that is y5 and y6 you will have to compute. So let us take the first pattern. The first pattern is 0 0. So your P1 is 0 0, that is your x1 and x2 both are 0. If that is the case, then you compute y3, that will be phi of 0, and since this is the step function, this will be equal to 1. Phi of 0 is equal to 1. Similarly, if you compute y4, again your x1, x2 both are 0. So this will also become phi of 0, and this will be equal to 1. Now these y3 and y4 are the inputs for the node 5 and 6. Right. So based on these inputs, you will have to compute y5 and y6. So if you take y5, that is phi of y3 minus y4. So both are 1. So that is also phi of 0, that is 1. Similarly y6, since again y3, y4 both are equal, you will have phi of 0, that is equals to 1. These two are your final output. So for the pattern 0 0, you are getting the output as 1 1. Okay. Similarly, if you take the next pattern, which is 1 0. Let me take a new slide, and we will also copy this equation so that it is easier. So y3 is phi of minus 2x1 plus 3x2. y4 is phi of 4x1 minus x2. y5 is phi of y3 minus y4. And y6 is phi of minus y3 plus y4. Now let us take the second pattern, P2. P2 is 1 0. 1 0. So x1 is 1 and x2 is 0. So if you put that in y3, you will get phi of minus 2, because your x2 is 0. So, that will be equal to 0. Okay. And your y4 is phi of 4, that will be equal to 1. Now, using this y3 and y4, you compute y5 and y6. So, your y5 is phi of y3 minus y4, that is minus 1, that will be 0, and y6 is minus y3 plus y4, which is phi of 1, that is equal to 1. This is your final output for the pattern 1 0. So, for the pattern 1 0, your output is 0 1. Then the next pattern is P3. So, we have P3 is 0 1. P3 is 0 1. So, if you put that similarly, so y3 will be phi of 3, which is 1, y4 will be phi of minus 1, which is 0, then using this y5 will be phi of 1, which is 1, and y6 will be phi of minus 1, which is 0. So, your output is 1 0. And the last pattern you have is P4 is 1 1. So, if you put 1 1, then your y3 will be phi of minus 2 plus 3, right? Your both x1 and x2 are 1. So, this y3 will be phi of minus 2 plus 3, that is phi of 1, that is equal to 1. Then your y4 will be phi of 4 minus 1, that is 3. So, this will also be 1. Then you have y5, that is phi of y3 minus y4, both y3 y4 are 1. So, this will be phi of 0, that is again 1, and y6 is again phi of 0, which is equal to 1. So, this is your output 1 1. So, for the input 1 1, you get the output also as 1 1. y5, y6 both are 1. So, this is how you can compute the output for a multi-layer network also, where you have more than a single neuron. So, we saw how to compute the output for a single neuron. Then we formed a multi-layer neural network with multiple neurons in that, and we saw how to compute the output of such a neural network. So, these were the problems for today. If you have any questions, you can ask it. Okay, I do not see any questions. So, let us close today's session. Thank you for joining. We will meet again in the next week with the next set of problems.